students, we're going to go over the ideal gas law in this video. So make sure you find the page of notes for ideal gas law in your packet. And first off, we're going to compare ideal gas law to or ideal gases to real gases. So we started out the unit talking about the kinetic molecular theory and the behavior of gases. And when we were talking about the kinetic molecular theory, we were talking about how gases ideally behave when we have a specific set of conditions. Now, gases behave most ideally at high temperatures and low pressure, kind of like you guys do in the summertime. And it's really hot outside and you don't have the pressure of school. Anyways, it's very rare that we actually have those kinds of conditions. I mean, when you think about room temperature, this is not a hot temperature. So we have to have high temperatures and low pressures for gases to behave ideally. That's when they're traveling the fastest. We need to compare ideal gases and real gases. First off, in terms of gas movement, ideal gases travel in straight lines, but really, in actuality, gases do not travel in straight lines. They travel in random motion. Ideal gases are not attracted to other molecules. Real gases are attracted to other molecules. Now, we haven't talked about intermolecular forces yet. Intermolecular forces are going to be the attraction between one molecule and another molecule. Well, with ideal gases, the gases are moving so quickly and they're spaced so far apart that they don't attract to other molecules that are moving nearby them. But real gases, because they're not traveling as quickly, because they're not at high temperatures, when those gas particles get close enough to each other, they can have a slight attraction for other nearby molecules. And that's what ties into that next point about liquefying. Gases are gases because of their particles are so far apart and they're not attracted to each other. So ideally, gases can't liquefy because you can't form strong enough connections to pull the molecules close enough together to form a liquid. But really, when those gas particles get close enough together and the attractive forces can exist between the molecules, you can get strong enough attractions that those gas particles get close enough to each other that they can become a liquid. And then lastly, ideal gases, we talked about during the kinetic molecular theory that they do not lose energy during collisions. They're called elastic collisions. So they're going to keep moving at the same speed whenever they collide with the sides of a container or other gas particles. But in actuality, gases can lose energy during collisions. Now, what I would like you to do is on your own time, open up this PowerPoint in Schoology, click on this link over here, real gas versus ideal gas, and it's going to show you a little video. It's kind of goofy and kind of silly. It's going to make you laugh, but it does, I think, a good job of showing you and highlighting the differences between ideal gases and real gases. So what we're going to have to do is calculate properties and variables about gases using the ideal gas law. We call it PIVNRT, PV equals nRT. Now, when we use this, first off, in comparison to the combined gas law that we did previously in this unit, with the ideal gas law, there's only going to be one pressure and one volume and one temperature. Whereas in the past with the combined gas law, we talked about, a changing pressure or what's going to happen to the volume if we increase the temperature from this to this, or what happens to the volume if the pressure is decreased from this to this. And we would see two different pressures, or we could see two different temperatures, or it was asking for a new volume, indicating the volume was changing. So you really have to analyze your question to see, is it talking about, two of the same kind of variables? So I want to pick out one of the equations with a 1 and a 2 in it. Or is it talking about just one pressure, one volume, one temperature, in which case I'm going to use this equation, the ideal gas law. When you use this equation, you have to have pressure in atmospheres, you have to have volume in liters, you have to have temperature in Kelvin. And it tells you that right here on this picture here, which I've put in your notes. Okay, you have to have those kinds of units, and that's all because of the R value. The R value is a constant. It's your ideal gas law constant. And it is on the back of your periodic table on that reference chart. So it's not anything that you have to memorize. Neither is this equation. It's on the back of your periodic table. You just have to make sure you know how to use it. So your ideal gas law constant is going to be 0.0821. It has these units here, liters times atmospheres divided by Kelvin times moles, but you don't have to know those. It's on your periodic table. And seeing those units is going to help remind you, I've got to have the pressure in atmospheres. I've got to have the volume in liters. I've got to have the temperature in Kelvin. So let's take a look at what these kinds of problems look like. So when we look at this example here, so I'm trying to find my draw tool. When we see liters, that's indicating a volume, contains 0.60 grams, that's a mass, of oxygen at a temperature of, so that's a T. And we're going to be looking for our pressure. So you can see we only have one of each thing, which means we're going to have to use PV equals nRT. So the first thing we're going to have to do is convert that mass into moles, because we don't put mass in this equation, we put moles. So we have 0.6 grams of O2 times, we have put our molar mass down here, 32 grams of O2. And we have 1 mole of O2 up here on the top. So we're going to go ahead and calculate this really quick. And I'm not going to round to sig figs quite yet. I'm going to wait till the end, 0.01875. And those are going to be my moles. So I want to plug my variables into my Pivnert equation. I'm going to be looking for P, so that's my X. My volume is 5.0 liters. My moles I just calculated is 0.01875. My R is the ideal gas law constant, 0.0821. And my temperature has to be in Kelvin, so I have to add 273.15. Oops, I put the decimal point in the wrong spot. 273.15. So that's going to be 295.15. So I need to get my X by itself. So how am I going to do that? Well, I'm going to have to divide both sides by 5.0. Okay. And that's going to get me my X, which is pressure. So I'm going to take my moles, 0.01875 times ideal gas law constant times 295.15. I'm going to divide all of that by my volume of 5. Now my sig figs are going to be based off of whichever of these values has the least amount of sig figs. They all have 2 sig figs, so my answer is going to have 2 sig figs. So I'm going to round my answer to 0.091. Make sure you guys are doing this in your calculators to make sure you are getting the right answer and the same answer as me, so you make sure you're not making any kind of calculator mistakes. Because I was solving for the pressure and because I'm using the ideal gas law, my units are going to be atmospheres. Let's take a look at example 2. How many grams? So we're going to be looking for the mass of krypton are present in a 600 milliliter, that's indicating volume, container at 110 degrees Celsius, that's temperature. We have to add 273.15, in which pressure of krypton is 10.0 atmospheres, that's pressure. So again, we've got one of each variable, pressure, volume, temperature. We're going to use Pivnert, PV equals nRT. So my pressure is 10.0 atmospheres. My volume, because it gave me my volume in milliliters, I have to convert that to liters by moving my decimal point 3 times to the left. So that's going to be 0.600. I'm going to be solving for my moles. That's my X, because I'm looking for grams and I can go from moles to grams. My ideal gas law constant is 0.0821. And then my temperature is going to be 1283.15. All right, so how am I going to solve for my X? And I'm going to have to divide both sides by 0.0821 and 1283 because I got to get X by itself. This is going to allow us to cancel out those R values and cancel out our temperatures. That cancels and that cancels. Now, when you enter this into your calculator, you really have to be careful. Some of you guys are entering this into your calculator and it's only dividing by the first number and not the second number. So when you do this, what you might want to do is put this as in parentheses here, 0.0821 times 1283.15, close parentheses, to make sure you're dividing by both things that you want to divide by. And then I'm going to have for my answer rounded to 3 sig figs because all of my givens in the question have 3 sig figs. My X is going to be 0.0570. And this is moles because that's what I'm solving for. That's what N is. I need to solve for grams though. So that means I'm going to have to do a mole to gram conversion, 0.0570 moles. And this is krypton. And I got to have moles on the bottom here. And use the molar mass of krypton up here on the top, 83.80. So I'm just going to go ahead and multiply those together. And rounded to 3 sig figs, I'm going to get 4.77 grams of krypton. How many atoms is that? Well, I'm going to go back to my moles. So if I start with my grams, I'm just going to have to do more steps. So I'm going to start with my moles. Moles of krypton. Instead of using the molar mass this time, I'm going to use Avogadro's number, 6.02 times 10 to the 23 atoms. We're just going to do that. And I should be getting for my answer 3.43 times 10 to the 22nd atoms of krypton. And that's it. Let's go ahead and take a look at the next example here. I have a balloon. Oh, on this one, I did change the sig figs in my example here from what's on your paper. So just FYI on that one. I hate 1 sig fig questions. I have a balloon that can hold 100 liters. Since it's liters, that's talking about volume of air. If I blow up this balloon with 3.00 moles, that's my N, of oxygen gas at a pressure of 841, mmHg, that is pressure. I don't know what I was doing there. Let me erase that. That looks silly. Pressure. What is the temperature of the balloon? So I'm looking for, that looks silly too. Looking for temperature. So I've got one of each variable, which means I'm going to use PIVNERT. PV equals nRT. Now, before I can use PIVNERT, I'm going to have to convert my pressure into atmospheres because I have to have atmospheres for my pressure. So I have 841 mmHg. Remember, your pressure conversions are on your reference chart on the back of your periodic table. So the constant for mmHg is 760, and that is equal to 1 atmosphere. So I've got 841 divided by 760, and that's going to give me 1.11 atmospheres. So now I can plug that into my PIVNERT, 1.11 atmospheres. My volume is going to be 100 liters. My N, my moles, is 3.00. R is a constant. Remember, it's 0.0821. And I'm going to be solving for my temperature, so that's my X. So how am I going to get X by itself? Well, I have to divide both sides by my 3.00 and my, 0.0821, because I got to get X by itself. So when you're plugging this into your calculator, remember, you might want to put some parentheses around these two numbers that you're dividing by, so that way you can make sure that the calculator is going to divide by both numbers. And I'm going to get for my answer Make sure you're plugging this into your calculator and checking yourself. 451, because I get 3 sig figs. And that's going to be in Kelvin because I'm solving for my temperature. And when you use ideal gas law, the temperature is in Kelvin. Let's take a look at number 4. If I have an unknown quantity of gas at a pressure of, so this is pressure, a volume of, and a temperature of, that means I have to add 273.15. How many moles of gas do I have? That's what I'm solving for. So I've got one of everything, which means I use PVNRT. PV equals nRT. What are you going to have to do before you can use PVNRT? You have to convert your pressure into atmospheres. So look at your reference chart so you can see what the constant is for kPa. And that's going to be 101.3. That's 1 atmospheres on the top. So I just divide those two things together. Oopsie. And I get 1.200 atmospheres. And then I can go ahead and plug that into my PVNRT, 1.200. And then my volume is 31 liters. My moles is going to be my X. That's what I'm solving for. R is my constant, 0.0821. And then my temperature is going to be 273.15 plus 87. I get 360.15. So how am I going to solve for my X? How do I get that by itself? Well, I have to divide both sides by my gas law constant and my temperature. And again, when you plug this in your calculator, you may want to put some parentheses around those bottom numbers so you can make sure you're dividing by both numbers. Okay, so I take my pressure times my volume divided by my gas law constant and my temperature. And I should get for my moles, and I only get 2 sig figs because of my volume there. It has the fewest number of sig figs, just 2 sig figs. I get 1.3 moles of gas. And for this one, I can stop there because it only wants moles. It doesn't ask for grams or atoms or anything like that. Let's take a look at our final example. It says volume, so we're looking for volume. And it says 20 grams, so that's a mass of argon occupied STP. This doesn't look like a whole lot of information. But you want to remember STP is telling us something. That's telling us that the temperature is 0 degrees Celsius and the pressure is 1 atmosphere. So that means our temperature is 273.15 Kelvin. So it gives us a temperature and a pressure. We're trying to find the volume. So we're going to be using PVNRT because nothing is changing. We're going to have to convert our grams of argon, though, into moles of argon by using the molar mass of argon. I dropped my periodic table, but I think it's 39.95. Yeah. 39.95 grams of argon. It's going to be close to 0.5. Actually, it's 0.01 if you want to get technical. Moles of argon. Okay, so let's plug everything into our PVNRT equation. Our pressure is 1 atmospheres. We're not going to use these constants for sig figs. We're not going to use these constants for sig figs. Our volume is our unknown, so that's X. Our moles we just calculated, 0.501. Our R is going to be our gas law constant, 0.0821. And our temperature is 273.15. Now, because our X is on the left side, we want to divide both sides by 1. Don't really have to do that. But I'm just showing you in case it's something other than 1. So we just have to really multiply those numbers on the right. And we're only going to get 3 sig figs. This is our only number here that was given to us. That's our only measured value. So it's going to give us our sig figs. So we have 11.2. And we're solving for volume. So the units for volume here are going to be liters because that's what we use in the ideal gas law for volume. And that's how we do ideal gas law calculations. So give it a try. Let me know if you guys have questions and how I can help. Okay.